Myself Srinivasan, working as a faculty in the Department of Mechanical Engineering at Sri Srinivasa College of Engineering and Technology. In the last lecture, we started to discuss about sequential modeling. In that, we discussed recurrent neural network, and we have to update the weights across all the hidden states. Okay, so for that, we will use whatever we have studied in the previous lectures on backpropagation. Okay, so today's topic is all about backpropagation through time, BTT. And it is algorithm which is applied all the time steps, so that's why it is called backpropagation through time. So if you look at this diagram, and we have three weights. This is the initial input weight, and this is the weight this is the weight for the hidden state, and this is for the weight for the output layer. Okay, so earlier in the earlier lectures we said, and the U is basically basically the input weight, and the corresponding bias weight is Bx. So that is the notation we have used. So slightly we modified the notation. There here we used W naught and B naught. So that is not going to happen here. It is not going to be here. And here in WH we have used in the previous lectures. Now we are going to put only W. So we have three weights. One is U, W, and V. So we are going to update the weights, because when you have error, we have to update the weights to get increase the accuracy of the predictions. So that's why we use the backpropagation through time. Okay. So if you look at, these are the inputs, x1, x2, x3 are the inputs for the different time steps, and these are the hidden states, and this is E1, E2, E0, E1, E2, E3, E4. These are all errors. Okay. So now we are in the position to update the weights of W, and we are in the position updates of W, and we have to update the weight of U. So these are three weights to be updated using gradient descent algorithm. Okay. So basically, if you look at this RNN structures, here we have summation and activation. So here we use Stanage activation function. Here we have a summation and linear activations. ReLU, we use ReLU over here. Okay, so here summation activation happens here. Once again we apply summation and activations. Okay, so when we look at this y hat is basically a predicted one, and based on this we will calculate the error. Okay, error is basically y hat, that is a predicted one, and the true one, the actual one. Okay, so this is this is represented over here, E0 in E1, E2 and all. Okay, so if you look at this, we wanted to change the weight of V. Okay, so what we have to do is dou E3. If you look at this particular hidden state, so dou E3 divided by dou V is basically a single step that can be done by using this way. So what we are doing here is that dou E3 divided by dou y hat 3. Okay, this is a 1. Okay, here this is a 1. Okay, so this is a 1. Okay, again this is a y hat 3 is basically activation of this. Activation will when you apply activation function on the summed product, summed one, and you will have a predicted output. Okay, so you have to differentiate that function. So dou E3 divided by dou y hat 3, again dou y hat 3 divided by dou V. Okay, so the dou V is basically, I can write in terms of, this is the activation function, this comes from the activation, this comes from the summation term. Okay, so again the summation term can be differentiated with respect to V. Okay, so finally we can write dou V by dou E3 divided by dou V. So dou E3 divided by dou V is basically depends on the activation function that we use on the summed term, and again differentiation with respect to the summed product, again with respect to the weight given in this time step. Okay, so if you do these things, you will get dou e3 divided by dou v. And this is the case for the error calculation with respect to the change in error with respect to v. So similarly, we have to calculate for the case of w. For the case of w, and the error 3 is basically, this is error 3. So this error 3 is basically depends on dou e3 divided by dou w depends on the two things. Okay, so you have to do it. It depends on the it depends on the hidden state values. So if you look at this time step from K0 to K3, so dou E3 divided by dou hat 3, and again dou hat 3 divided by dou h3, this one actually, then again dou h3 divided by dou hk. So this k represents from the hidden, all the previous hidden states. This is basically previous hidden states. Okay, previous hidden states. Okay, so this depends on the previous hidden state. Then dou hk divided by dou w. So this can be written by this way. Okay, so what we have summation term, and we have a product term over here. So this summation term is basically from the whatever the error predicted one, and this summation term whatever is in the hidden state. Okay, so this is a based on, because of this we may end up with gradient problems. We may end up with vanishing gradient problems or exploiting gradient problems, because we have many gradient terms that is being multiplied over here. Okay, so as a result we will end up with vanishing gradient issue, either gradient issue or exploiting gradient issue. Exploiting gradient issue. So these are the things we come across. So what we are supposed to do here is that we have to differentiate with respect to v, and we have to differentiate with respect to w. We have to differentiate with respect to u. So when you backpropagate, and the loss of information is this way, and you are going to backpropagate the error. Okay. So this is the way it works in RNN architecture. So whenever we have a small gradient, the value of the gradient is very small, we may end up with vanishing gradient. The weight update is very huge, we may end up with exploiting gradient issue. Okay, very small, less than 1. For example, if I say Eigen values or W is very small, we may end up with vanishing gradient, and the Eigen value of W is going to be large, we may end up with exploiting gradient issues. So these are the two issues that may come across in RNN architectures, particularly while performing backpropagation. Okay. So this in RNN, it is very difficult to handle more than 20 words. Okay, it cannot be used for long range. It can be used for the short range. So even if you use short range, we may end up with vanishing gradient problem or exploiting gradient problem. Okay, since we go for the multiplication of repeated gradients, and the product multiplication of gradients, and it is going to be it may end up with a huge value. Okay, so these gradient problems are depends on not depends on the direction. It all magnitude based. Okay, so it tries to reduce the error, as we have seen in the couple of lectures back. So it is always move towards the to move towards opposite direction of the gradient. Okay, so when you have the gradient is very huge, we may end up with exploiting gradient problem, and as a result it may lead to instability. It may lead to instability. It is not, numerically it is not going to be stable at all. Okay, numerically it is not going to be stable at all. So because of the exploiting gradient problem, then it is going to be very huge. Okay, so when vanishing gradient problem, that when you have vanishing gradient problem, the W is very less, and the network will not learn anything. But when you have a huge problem, huge the weight is the weight update is huge, then as a result, it may lead to avoid exploiting gradient problem, we can use a norm-based gradient clipping. So in that we can use this formula, that is a norm-based one, and this is a tau is basically a threshold. So when you use this new gradient, and even though the gradient is the weight update is huge, and weight update is very huge, and when you use this formula, you can get a small value of g. So that will lead to the stability of the network. Okay, so stability of the network, that is the advantage of using this gradient clipping. So whenever we work on the deep neural network, we can use this any of the initialization. One is the key initialization, and another one is that is for the case of ReLU function. Whenever you use ReLU activation function in the deep neural network. So when you use this tanh and sigma activation from the deep neural network, we can use this Xavier and Gloart, and when you use this RNN, we can go for this orthogonal initializations. So even though if we use this weight initialization, we can delay the gradient issues, but we can't solve the gradient issues. So in order to solve the gradient issues, we have to move forward towards LSTM. So that we will see in the next lecture.